Welcome to our very last seminar and talk of the year. We won't have another one this year. I'll say more at the end, maybe. But yeah, today we're very happy that Kevin is talking, Kevin Hendrey from the Institute for Basic Science in Korea, and he will tell us about obstructions for bounded branch depth in matroids. Yes, all yours.
Okay, thank you very much. I didn't know I had the honor of being the final seminar speaker for the year, but thank you. Yes, so my talk will be on obstructions for bounded branch depth in matroids. So joint work with Pascal, Colin, Dylan Mayhew, and Sang-Il and I'd like to particularly thank Pascal because a lot of these slides he wrote because he's already given a talk on this paper. All right. So let's start. So first, I'll just quickly go over. So a matroid consists of a ground set together with a collection of subsets of the ground set, which we call the independent sets. But the independent sets need to satisfy three axioms. So firstly, the empty set is always an independent set. So the collection of independent sets is closed under taking subsets. And finally, there's what's often called the augmentation property, I think. So if you have two independent sets, x and y, and the size of y is strictly bigger than the size of x, then there's some element in y which is not in x, which can be added to x to preserve independence. Okay, so some examples of independent sets. So if you take an arbitrary set of, take the ground set to be an arbitrary set, then you can just take all of the subsets of size at most k for any integer k. And this will give you a matroid. It's not too difficult to see that all of these properties will be satisfied if you just take all sets with a bounded size for a fixed constant. And these are called uniform matroids. And the second example is perhaps what it sort of motivates the terminology of independent sets. So if you have a set of vectors from any vector space, and you let the independent sets be exactly the linearly independent sets of vectors, then this always gives you a matroid as well. And we call matroids that you can construct this way, we call them representable matroids. And finally, as the last example I'll give here is that you can construct a matroid from any given graph. So if you have a graph, then you take the ground set to be the edge set of the graph, and you take the independent sets to be the forests in the graph. So any subforest of the graph is an independent set. And it's a little trickier, but you can sort of think about it and convince yourself that all of the three properties will still be preserved for independent sets defined this way, no matter what graph you start with. Okay, so these are sort of perhaps the three classes of matroids that it's most important to know about for the moment. Okay. So here are some basic definitions. So a circuit of a matroid is a minimal dependent set. So if we consider the uniform matroid, so where you take the independent sets to be sets of size at most k, then a circuit is just any set of size k plus 1. Because it's the minimal non-independent set. And then a base is a maximal independent set. So this comes, the terminology is the same as for vector spaces, really. But if you consider the example of graphic matroids, so where I said that the independent sets were exactly the forests. So if you start with a connected graph, then the circuits of the graphic matroid will correspond to the cycles of the graph, because a set of edges forms a forest if and only if it doesn't contain a cycle. And then a base of the graph, so a maximal forest, well, that's just a spanning tree. So the bases of the graphic matroid will be the spanning trees of the graph. And then finally, so the rank of a set of elements of the ground set is equal to the largest, the size of the largest independent subset of X. Was there a question or? This, no, cool. Okay, so using the rank function, we define what we call the connectivity function of the matroid. So this function, so lambda of X is just equal to the rank of X plus the rank of the complement of X minus the rank of the entire matroid. So the rank of the entire matroid will just be the size of the base of the matroid. Okay, so yes. So now I'll quickly go over Matroid Minors, just in case anyone hasn't seen this before. So if we let C be the set of circuits of a matroid, and we consider an element of the ground set, well, there's two ways to remove E from the ground set to find a minor. So we can delete the element E. And when we delete E, we remove E from the ground set and also just remove all circuits that contain E from the set of circuits. Or instead, if we can contract E. And when we contract E, we remove E from the ground set and also remove E from all circuits that contain E. So we'll have to be a bit careful here. So we're not allowed to do this if the set E is itself a circuit, because the empty set is never allowed to be a circuit. Okay, so this will give us a new set of circuits, and this set of circuits will define a new matroid. So a minor of a matroid is any matroid obtained from a series of deletions and contractions, with the restriction that the set of contracted elements must form an independent set. And if you consider graph minors, so so if you take a minor of a graphic matroid, then it will correspond to the graphic matroid of a minor of the graph. So it sort of generalizes minors of graphs in this way. Okay, and another sort of basic definition. So if we consider the set of bases of the matroid, so the maximal independent sets, then there's a notion of duality. So the dual of a matroid is the matroid whose bases are the complements of the bases of M. Okay. And this has some nice properties when you look at minors. So the dual of a minor of a matroid is a minor of the dual of the matroid. And also what's nice is that a matroid and its dual have the same connectivity function. So for any set X in M, the connectivity, so lambda X will equal lambda M dual of X, which it's a simple consequence of the definition of the connectivity function. Okay, so I'm going to define the branch depth of a matroid, I'll start by defining the branch width of a matroid. So we say that a decomposition of a matroid consists of a tree, so an arbitrary subcubic tree, so maximum degree at most 3, so maximum degree 3, and a bijection from the the ground set of the matroid to the leaves of the tree. Okay. And we're going to say that a partition of EM of the so if you partition the ground set of the matroid, we'll say that this partition is witnessed if there's an edge of the tree separating the image of X from the image of X complement. So let me draw a picture. So let's draw some subcubic tree. Can everyone see what I'm drawing? Hopefully, yep. Okay, so if we sort of separate the leaves into two sets like this, then there's an edge of the tree, this edge here, which separates these two sets of leaves into two separate components. So we say that this is one of the separations witnessed by this decomposition. And you sort of see that, yes.
Kevin, is this a rooted tree?
It's not important for at the moment, not yet. So there will be a later thing where there will be a rooted tree, but not for this one, I think. Yeah. So yeah, we can delete any edge from this tree, and we'll get some partition of the leaves, and we'll say that those are the partitions that we're interested in. And why are we interested in these partitions? So the width of the decomposition is the maximum value of lambda of X, such that X is given by one of these, so XX complement is one of these partitions. And then the branch width of the matroid is the minimum width of a decomposition of the matroid. Okay, so this is sort of motivated by the notion of tree width for graphs. So if you take a graphic matroid, then the branch width of the graphic matroid and the tree width of the associated graph are tied. So one is bounded by a function of the other. So if one is large, then the other must also be large. So in this sense, it's a nice generalization of tree width to matroids. Okay, so let me just erase that picture quickly. Cool. All right, so well-known theorem of Robertson and Seymour. So if a graph has large tree width, then it must contain an n by n grid as a minor. But since branch width and tree width are tied for graphic matroids, we could also say that if a graphic matroid has large branch width, then it must contain a minor, which is the matroid of an n by n grid. But this turns out to be true more generally. So remember I mentioned representable matroids, which were just given by sort of sets of vectors, sort of some vector space. So if you have a finite field and you take matroids representable over a finite field, then it's also true that if the matroid has high branch width, then it still must contain a cycle matroid of the n by n grid as a minor. So this sort of it's a sort of generalization of the grid minor theorem for graphs of large tree width. But there's a broader conjecture which gives a more complete, or suggests a more complete characterization of what exactly forces a matroid to have high branch width. So there's three possibilities. So either a matroid has high branch width because it contains the cycle matroid of the n by n grid as a minor, or perhaps it contains what's called the bicircular matroid of the n by n grid or its dual as a minor, or it contains a uniform matroid with two n elements where the independent sets have size n for some large value of n. So this would be a nice characterization for the obstructions to having bounded branch width.
I'm sorry, can I ask?
Yeah. Yes.
I missed something. I think what's
yes.
the cycle matroid and the bicircular matroid? I think one of them
Right.
I can figure out. But...
Yeah. So the cycle matroid is, so when I said the graphic matroid that I defined earlier, so this is sometimes called the cycle matroid of the graph. So you just take the independent sets to be subforests. The bicircular matroid of the n by n grid, I think you take, I think the circuits are minimal connected subgraphs that contain two cycles. I think that's the bicircular matroid, but I actually might have that wrong. But I'm pretty sure it's that. If someone else knows better, then they can correct me.
I just thought I missed the definition.
No, yeah, I didn't define this. This won't be important. So this is just a sort of, oh, great. So excellent. I have confirmation. But yeah, I just wanted to sort of present the idea that there might be a more complete characterization. I think I've got this one. Cool. All right. So so the tree depth of a graph is the minimum number of steps needed to delete all the vertices of the graph if at every step you're allowed to delete one vertex from each component. Or equivalently, the tree depth of a graph is the minimum height of a rooted forest such that G is a subgraph of its closure. So what does this mean? So let me draw a nice graph. So maybe the graph is a path. So that's a good number. So let's suppose that I want to delete all of the vertices of this path. So at the moment, this graph has one component. So the rule is that I'm allowed to delete one vertex in the first step. So let me delete this center vertex here. But when I delete this vertex, now I split it into two components, which means on the second step, I'm allowed to delete two vertices. So let me delete this vertex here and this vertex here. And now I've split it into four components, which means on the final step, I'm allowed to delete all four vertices. Okay, so the tree depth of this path is 3 because I had to use 3 different colors, one for each step. So what's the equivalent definition? So the closure of a tree. So this is so if you take, I'll just do a rooted tree. So I have this root at the top, and let's suppose that I have. So let's say this is a tree of height 3. Okay, so the closure of this tree means that we add an edge between every vertex and all of its ancestors. So here, this just means that everything is adjacent to the root, because the root is an ancestor of every vertex. And what we see here is that this path is a subgraph of this tree that I've just drawn. And that means that the tree depth, again, of this path is at most 3. And this turns out to be optimal in both cases. So this is really the tree depth of this path. And it turns out that the only reason, in some sense, that a graph ever has large tree depth is because it contains some long path. So if a graph contains a long path, then it has to have large tree depth. But also, if a graph has large tree depth, then it must contain a long path. Okay, let me just clear that. All right. So sort of as an attempt to generalize this, so I should mention, this is the definition of branch depth that I'll present is not the only definition of branch depth that's out there. So Kadosh, Kral, Leibniz, and Mark introduced an alternative definition of branch depth, which also has a lot of nice properties and is very interesting. But I won't talk much about that one today. So the notion that I'll present, is as follows. So let's redefine a decomposition of a matroid. So here, yes. So now the tree should be a rooted tree. Or I guess it sort of doesn't matter, but it's nice to think of it as a rooted tree. So before we took the tree to have maximum degree at most 3. Now we allow the tree to have arbitrarily high max degree. And again, we take a bijection from the elements of the matroid to the leaves of the tree. Now, if this was the only restriction, then what you could do is you could sort of map all of the. You could take the tree to be a star, say, and then all of the separations that you would get from the earlier definition would just be separating one element from the rest of the elements. So all of these separations would have low connectivity value. So we need to change something about the definition to sort of stop that decomposition from working. So we now look at a different class of partitions. So we say that a partition is witnessed if there's a vertex separating the leaves corresponding to X from the leaves corresponding to X complement. So maybe I'll draw some decomposition like this. So now I can take a decomposition. I can take a partition that looks like this, and there's this vertex up here, which separates the blue sets from each other. But I'm going to get more partitions than I had before, because I could. So if I delete this vertex, I split it into really 4 different components, and I can sort of sort them into two buckets any way that I like, and still find a partition which is witnessed by this decomposition. But again, with this new notion, then we define the width of the decomposition sort of the same way. So the width is still just the maximum value of the connectivity function of a set, such that X complement is witnessed, but we redefine what it means for the partition to be witnessed by the decomposition. So if we still took a cubic tree, then really this wouldn't make any difference. So if the decomposition still happened to have a tree which was subcubic, then the partitions that are witnessed in the first sense of deleting an edge actually are exactly the same as the partitions that are witnessed by deleting a vertex. So deleting this edge witnesses, so if I delete this vertex, then there's 3 partitions that you can take, but all of them are actually witnessed by one of the edges. So it only really makes a difference when the decomposition has vertices of higher degree. But the reason that you want to take vertices of high degree now is that now we care about the radius of the tree, or the height of the tree, if you think of it as a rooted tree. So we say that the branch depth of the matroid is equal to the minimum value of D, such that there's a decomposition in this new sense, such that the width and the radius are both at most D. So there's sort of a trade-off. If you have high degree vertices, then you'll have more separations to consider, but the tree will have lower radius. But if you have, if you have low degree vertices, then there's fewer separations to consider, but the radius will be higher. Okay. And maybe I'll mention a couple of nice properties about this notion of branch depth. So if you take a minor of a matroid, then the branch depth never increases. And since it's defined in terms of this connectivity function, actually, if you take the dual of a matroid, then the branch depth stays the same. Because the connectivity function of the dual is equal to the connectivity function of the original matroid. Okay. Right. Also, the branch depth of a matroid is at least equal to the branch width of the matroid. So it's a simple lower bound. So if you consider the branch decomposition for the branch depth, if you consider the decomposition for the branch depth, you can sort of split the vertices apart into subcubic vertices and not create any new partitions. So that's true. Also, it has. So I mentioned that it's sort of motivated by the tree depth of a graph. So this is sort of justified by this statement here. So the branch depth of a graphic matroid. So this is the cycle matroid of the graph, and the tree depth of the graph are tied if the graph is 3 connected. So a 3 connected graph has large branch depth, tree depth, if and only if its matroid has large branch depth. Okay. Right, so I'll go on a bit of a tangent now. Yes, so the fundamental, so if you have a base of a matroid and you take an arbitrary element which is not in the base, then there's a unique circuit if you consider the union of the base and that element. And that circuit is called the fundamental circuit of E with respect to B. It's not too difficult to see that it should be unique. If you consider trees, if you add one edge to a tree, you're always going to create exactly one cycle, for example. So using this notion, we can define what we call the fundamental graph of a matroid. So with respect to a particular base. So this is a bipartite graph. So we have bipartition B and E and B complement, say, for the base B. And we say that an edge from, so the neighborhood of a vertex which is not in the base is just equal to the set of things in the fundamental circuit of that of that element. Okay, so I'll give an example. It's got this nice property. So if you consider binary matroids, then you can actually sort of recover. If you know that a matroid is a binary matroid, then you sort of recover all of the information from the fundamental graph up to duality. Okay, so I'll give an example though. What if we start with a graph? So this is the fan graph. So it's just consists of a path plus one dominant vertex, and we're going to yeah. So if we take the spanning tree as the base of this graph, so if we take a star, so yeah, remember the base of a graphic matroid for a connected graph is always a spanning tree. So this star is the spanning tree of this matroid. Sorry, the star is the spanning tree of the graph, so it's a base of the matroid. And for every edge which is not in the base, there's, so if I consider this blue edge here, then the fundamental circuit is going to be a triangle. So for this blue edge, it's sort of this triangle here. Okay, so what does it mean if I start to draw it? So let me draw some blue edges. So 1, 2, 3, 4, 5, 6, I think I have. Okay, so each blue vertex here is going to be adjacent to sort of the incident red edges. So, oh dear, sorry. So what's going to happen is that this fundamental graph is going to look like a path. So maybe I can number these to make it a bit more clear. So if I number the things in this clockwise order, like this, and I number the blue edges in the same clockwise order, then you can see that each blue edge should be adjacent to the two edges of this triangle that it forms, this wedge that it forms within the fan. And so the fundamental graph that you obtain when you draw in all these edges is this path. So hopefully that makes sense. Any questions? Maybe I'll clear that. Okay, yes. So sort of using this idea in the proof that Kwon, McCarty, and Wallen showed that for every n, there's some d such that every binary matroid of branch depth at least d contains the fan matroid as a minor. Yeah. Right. So now we get
sorry,
to,
a question, Kevin.
Yes.
You say it's a corollary. It's a corollary of some result that you haven't mentioned, or
it is yes. It is a corollary of a result that I didn't actually mention. So what they actually show is so there's a notion called rank depth. And for binary matroids, the branch depth of the binary matroid is equal to the rank depth of the fundamental graph. So what their result, their theorem, I guess, that this is a corollary of, said was that if you have a graph, then I think if you take a graph with large rank depth, then you have a path as a vertex minor. And so I won't define vertex minors here, and I won't define rank depth here. But it turns out that ends up implying that if you have a binary matroid, then it contains the fan-matroid as a minor. So there's some way of, for binary matroids, there's a way of translating between the fundamental graph and the original minor, the original matroid. So you can prove results about graphs and about these fundamental graphs, and then they have implications for the actual matroids that you're interested in. So that's why this is called a corollary here. Yeah. Okay, so conjecture of De Vos, Kwon, and is the following. So the conjecture says that for every n, there's some value of d such that every matroid of branch depth at least d either contains a fan-matroid as a minor, so a large fan-matroid, or a large uniform matroid, u to n to n. And our main result that I'll talk about today is a step towards this. So what we were able to show is that for every n and w, there's some d, such that every matroid of branch depth at least d either contains a fan-matroid as a minor or has large branch width. So I mentioned before that the branch width of a matroid is always a lower bound for the branch depth of a matroid. So every matroid with large branch branch width also has large branch depth. So in some way, this gives a necessary and sufficient condition for a matroid to have large branch depth. Okay. So, but before I get into that proof, I'll say a few more things about fundamental graphs, because they were very useful for our proof. So let's see. Suppose that we have a base of a matroid, and we consider some edge of the fundamental graph. Then if we consider switching u and v, so remember every edge of the fundamental graph will go between some element of the base and some element which is not in the base. So taking this symmetric difference with this edge will actually correspond to a base exchange. So after we perform this base exchange, we get a new fundamental graph, because the fundamental graph is defined in terms of the original base we took. So the question is, what does this fundamental graph, this new fundamental graph, look like if we just swap a pair of elements, so one element into the base and swap one element out. And it turns out that there's a lot we can say about what the new fundamental graph will look like in this case. Firstly, the elements that get swapped, for example, the element u, the neighborhood of u in the new fundamental graph will essentially be the same as the neighborhood of v in the old fundamental graph. Of course, u is adjacent to v and u is not adjacent to itself. If you have some element which is not a neighbor of u or v, then its neighborhood won't change. And if you have some element which is a neighbor of u, and it's in the neighborhood of v minus the neighborhood of and y, yes, right. So you've got two elements, x and y. One is in the neighborhood of u, the other is in the neighborhood of v minus the neighborhood of x. Then we know that xy will be an edge of the new fundamental graph. But these three rules aren't enough to completely tell you what the new fundamental graph will look like based on the old fundamental graph. But if we add this fourth rule, then it is enough. So if we consider a cycle of length 4, then the edge xy is in the new fundamental graph if and only if the symmetric difference of b and xy uv is also a base of the matroid. Okay, so this is all a bit complicated. But so the point of saying this is, so if you just know the fundamental graph of a matroid, but you don't know what the original matroid is, and someone wants you to perform a base exchange and come up with a new fundamental graph, so just swap one element out of the base and swap one element into the base, then a lot of the time, in some cases, you're going to be able to say what the new fundamental graph is going to look like, but not completely, because if you have a cycle of length 4, then there's some edge which you won't know what to do. But if you also know all of these sets, x, y, u, v, such that the symmetric difference of b and this set is a new base of the matroid, then you can completely determine the new fundamental graph from the old fundamental graph. Okay, so somehow, if we want to look at matroids in terms of their fundamental graphs, we sort of want to keep track of all of the sets which correspond to base exchanges, because then we can recover all of the information for the matroid. So this sort of motivates what we call twisted matroids. So we say that W consisting of a ground set and a collection of subsets is a twisted matroid if there's some matroid such that so the ground set of the matroid is also E, and F consists of all the sets B prime symmetric difference B for all of the bases B prime of the matroid. This sort of tells you all of the ways that you can exchange bases. So if you want to if you want to change one base to another base, you can use any of the sets in F to do it. This is sort of what the set F is keeping track of. So we write that W equals M asterisk B. So I call this the twisting operation. And we call the sets of F feasible. So F is I just called the feasible sets of the twisted matroid. And we can, let's see, yes. But we don't have to define the twisted matroids in terms of matroids. We could, if we wanted to, set up the twisted matroids independently. And if you wanted to do this, then it would look something like this. So now the empty set is always a feasible set. And if you have two feasible sets, and you consider any element in their symmetric difference, then there's another element such that the symmetric difference of F1 and EF is still feasible. And thirdly, so there's some set B, which sort of corresponds to the base from the matroid in the matroid definition, such that for every feasible set, the intersection of B with the feasible set is equal to the intersection of the feasible set and B complement. Yeah, so these are just sort of what happens to fall out if you translate bases of matroids to twisted matroids. Okay, so we'll quickly define minors of twisted matroids. So I think I should go a bit quicker. So we say that if M prime is a minor of M, then the twisted matroid M prime twist B prime is a minor of M twist B for any bases B prime and B. And if B prime happens to be equal to the intersection of B and the ground set of M prime, then we say that M prime twist B prime is the restriction of M twist B to the ground set of M prime. Okay, so this twisting operation that I mentioned, if we twist a twisted matroid by an arbitrary subset X of E, then what it means is that we keep the same ground set, but we replace the set of feasible sets with this collection of the sets F symmetric difference X, such that F is feasible. And this turns out to be a very nice operation. So let's suppose that we start with a twisted matroid corresponding to a particular matroid with a particular base B. So if we twist W with respect to a base of M, then what we get back is essentially the original matroid. So we get the set of bases of the matroid back. If we twist with respect to another feasible set, then we get another twisted matroid back with respect to the same matroid. And if we twist with respect to the dual of the base of the dual of the matroid, then we get back the that should say we get back the dual matroid. So we get the set of bases of the dual. So the nice thing about twisted matroids is that they contain almost all of the information of the matroid, except they can't distinguish between matroids and their duals. So they have this nice symmetric property. Okay. So going back to fundamental graphs, so fundamental graphs for twisted matroids just correspond to the graph whose edges are the feasible sets of size 2. So this turns out to be equivalent in some way to the previous notion of fundamental graph that we had. Okay, yeah, I'll try and go a bit more quickly. Right, so yes. So a minor okay. So under certain conditions, so if, yeah, I'll maybe skip over a couple of things, but if you have two matroids and their fundamental graphs are the same, and the fundamental graph has no cycle, then the two matroids are the same. And this is really interesting because the matroid that we're interested in is this fan matroid, and the fundamental graph of the fan matroid, if you remember, is a path. So what this means is that in order to find the fan matroid as a minor, sort of all we have to do is find a minor whose fundamental graph looks like a path, and we don't actually need to pay attention to anything else in some sense, because as soon as we find the right fundamental graph, we know that we must have the right matroid. Okay, so here's what we actually know. So if a matroid has a minor isomorphic to Fn, so this happens if and only if there's some minor and some base, or even actually if there's some base of the original matroid, such that there is an induced path, which is of length at least 2n-1. Okay, so here's a very rough sketch of the proof. So what we want to do is recursively find a structure that we're going to call a lollipop. So a lollipop consists of some path in the fundamental graph together at the end with a set with branch depth at least some b. Okay, and it's got two parameters, the length of the path and the branch depth of this end bit. Okay, so the reason this is useful, all right, so here's the formal definition. So it's just basically saying what I said there. Sorry, I'll try and rush through this a bit. Okay, so what we actually show is that every twisted matroid with sufficiently high branch depth and bounded branch width has a minor which is an AB lollipop. But a lollipop, an AB lollipop contains an induced subpath of length A. So if A is very big, then an AB lollipop already contains a large fan as a minor. Okay, so very, very roughly, maybe I'll draw a picture. And it's not going to really explain much probably, but let's see what I can do. Okay, so the way that we want to do this is by induction on A. So we want to construct, oh dear, that's not drawing. Sorry, I seem to have. Oh, have I lost connection?
We can still hear you.
Oh, you can still hear me. Good, good.
Yes.
So I was worried for
Yeah,
a
but
second
we
there
can't see
because
the drawing.
I
We can't see the drawing.
yeah, I don't seem to be able to draw at the moment. So sorry about that. So, yeah.
Maybe it got too hot.
Let me. Let's see. What's the?
It's nearly 4 o'clock, maybe.
Yeah.
Let's
Okay.
wrap up.
I was hoping to draw a very quick sketch, but then I couldn't draw. So, it's what we end up finding is some complicated recursive function, which looks something like this. And yes, if you define the function this way, then there's a way of showing that you can construct a large lollipop, which then guarantees that you have the fan-matroid of a twisted, yes, the fan-matroid as a minor. Okay, so sorry about the timing there. I think there you go. But yes, so maybe I skip to the end and say thank you.
Thank you very much. Let's all unmute and give Kevin a round of applause. Thank you.
I'll just leave it on the slide.
Maybe we have time for a very, very quick question.
I have a quick question. Is it easy to see that the bicircular matroid of a grid has a fan minor? Because then your theorem would imply the conjecture you want, assuming the large branch width conjecture.
Oh yeah, so sorry, this, yes. So I leave it on this slide, which I think answers your question. So the conjecture I mentioned earlier does in fact imply our conjecture, or not our conjecture, their conjecture. So is that what you're asking? So I think the answer to your question is yes, it is easy to see, well, maybe, yeah, somewhat easy to see that the bicircular matroid of the n by n grid does contain a fan minor. And therefore, the conjecture of Johnson, Robertson, and Seymour now does imply the conjecture of DeVos, von, and Hum by our.
Thanks.
Okay. Thank you so much.